So can somebody remind me, can you guys show me in the air what this function would basically look like? Oh shit. I'm like, we could, man. There. Can anyone else show me what's that? What would that look like? Do you guys? Yeah. Okay. So this book talks about toolkit functions, right? It talks about it's incredibly important that we know the basic shape of all these different functions, because then if I want to graph something that's been shifted, I just graph the base function and then move it. I don't have to make a brand new XY table and do it into that crap. I can just move the one that I know. Can somebody give me like some anchor points for this guy? Like, what should you plug in? What do you think you should kind of know? Okay, 1, 3. I'll leave some room. -1, good. No. What's the output for -1? What's 3 to the -1? No. What's the negative power mean? 4-letter word starts with F. You can say in mixed company. Flip. You guys with me? So negative power just means flip. So 3 to the -1 is 1/3. 3 to the -2, for example, is 3 squared flipped. 3 squared is 9, 1/9. It's that simple. If you see a negative power on something, think what it would be without the negative and then flip it. That's it. That's all a negative power is. So of course, what's a nice number right in the middle of those that's good to put in?
0.
That's crazy. What's 3 to the 0? 1. Okay, so those are my anchor points. 0, positive, negative. Those are good anchor points. Most functions, those work really well for as anchor points. What the hell do I mean when I say anchor points? Those are points I set, and then I pick them up and move them as my function requires me to move. Are you guys with me? So the base function, 3 to the x, 0, 1, 1, 3, and -1, 1/3. So I'll do it dotted because here's the function I really want to graph. I want to graph that function. Can anyone tell me about how that function will look different than that one? The shape will remain the same, but what changes? How does it?
It'll be 1 to the left.
Okay, left 1, and then 2 down. Because remember, transformation. Here's the beautiful thing about transformations, and we did so many transformations. I'm pretty sure most of you guys feel pretty comfortable with transformations. You literally just pick the points up and move them, and then redraw. It's hard to get better than that. And the fantastic thing is, everything you learn about transformations works no matter what the function is. We're going to learn like brand new functions you've never seen before, and then how do I move it? The same way as always. So how does this guy move? This guy moves left 1. Stay with me now. Left 1 and then down 2. So you literally just pick a point, pick it up, go to left 1, down 2. That point's now there. Left 1, down 2. Bam, bam. This one, left 1, down 2. 1, 2. So it's just barely above that. Can anyone tell me where the asymptote is for this one? Where's the asymptote for this one? This one. It's the x-axis, right? Y equals 0. Yes? So this one's got an asymptote here. Where's the asymptote going to be for this guy? So if I have an infinite bar and I move it left and right, that does nothing. It looks exactly the same. Looks the same. Looks the same. If we move it up or down, now that's very different, yes? And of course, what did I do? I moved everything down 2. So everything went down 2. So wherever the asymptote was, it's now 2 lower. So now there's an asymptote here, and you can see it makes sense. There's an asymptote here. You can already see these points trying to go closer to it, even before I drew it. So that is nothing new. There's nothing new there except the shape of the function we're working with. Moving it works exactly the same way. It could have been parabola, we would have moved it the same way. Square root, blah, 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 blah. So it doesn't matter what the function is. If I see a +1 in with the x, it's going to move whatever the shape of it is, it's going to move it left one. It's almost too nice to believe. So that's one thing, is shifting these guys. The other thing I want to bring up, this is brand new. What is our number system based on? Like, what are the place values of numbers? 4,567. The 4 is in the what place? 4,567. The 4 is in the thousands place, which is 10 cubed. The 5 is in the hundreds place, which is 10 squared. Base 10. I have no idea why. Why would it be base 10? Nobody could possibly know. Yes? If we had 8 fingers, we would probably have a base 8 number system, because when we were first little cave people running around, we had these to use to count things, yes? So if we had 8 of them, we would go 1, 2, 3, 4, 5, 6, 7, 10. 8 and 9 wouldn't exist. Let's not go there, I'm sorry. There's a whole other class that talks about different number systems, and it's really cool. Okay. I've lost my glasses. They're gone. Oh well. That's weird. Where'd they go? Oh man. No seeing. Did they even put them on? That's hilarious. Oh, there. Okay. Oh. Oh, that's what I wrote. Okay. So, here's the idea. Remind me what this is asking us. What is that question asking us?
What is 2 to what power?
Yes. So the output to a log is always a power. And that's going to become important later today. I'm hoping to get there. We'll see. All the properties of logarithms are the exact same as the properties of powers, because logs are powers. So this log represents the power 2 needs to become 8, and of course, what power is that? 2 to the what power is 8?
4.
Say what? No, 2 times 4 is 8. Log does not mean division. If it did, why would we create it? It's got to mean something different. Log says, what power does 2 need to become 8? Another way to say that is, how many 2's do you multiply to make 8? 3 2's multiply to make 8. 2 times 2 times 2. So here's the thing. We live in California. Sorry to shock you with that if you didn't know. What happens in California that doesn't really happen like where I moved from, Virginia? So I traded hurricanes for something else. Earthquakes. I like that. What were you saying? The UV, man. You're right. Back in Virginia, it rained a lot more. But here we got the earthquakes. How do we measure the energy of an earthquake? Yes, how do we measure that? Well, does anyone know what it's called? The something scale. The Rick. Rick and Morty. No, the Richter scale. Yes. Has anyone ever heard of the Richter scale?
Yeah,
A little bit, maybe. Because when they say there was a magnitude 7 earthquake, that's based on powers of 10. That's why a magnitude 7 is stupid powerful. And a magnitude 3, not that big of a deal. Because it's based on powers of 10. They're actually based on logarithms. And of course, why does that make sense what I just said? What's a log mean? What's a log always tell you? What's a log always? A power. So if the Richter scale is based on powers of 10, of course I'm going to use log to get the magnitude. It's powers of 10. What power does 10 need to measure the energy of this earthquake? So log base 10, this is the only time I'm ever going to write this. This is weird to me. I need you to understand. We never write this. This is equivalent to, I don't know if you've ever seen a triple equal sign. That's kind of like a definition. This is the same thing as this. So it's sort of like this. Do you guys, if I wrote this down, doesn't that look weird? Does that look weird to anybody?
Yeah.
Does it look a little weird to anybody? What did I do that I didn't need to? Well, that thing I just wrote, what did I do that I didn't need to? What's there that doesn't have to be there? The 2. If I don't write it, we know it's the square root. So why did math people, and the answer isn't because they're crazy, insane, and evil, why did they just not write the 2? Well, what's the most commonly used root? Square root. So we're like, we're going to save some time. We're just not going to write the 2. Do you guys, that's the sort of half sober, half drunk history of mathematics. That's basically how it was come up with. They're like, we're going to use this the most. Let's not put the 2. Save a little time. So if we see this symbol, we know it means the second root. We don't have to put the 2 in there. Same thing with this. What's the most commonly used logarithm? It's natural. We'll get there. But the second most is log base 10 because their number system is based on 10. So has anyone ever heard of decibels? Kind of like they always talk about, you go to a concert versus those things they use, jackhammers, to break up the road. They compare the decibels of the 2. And the old people like, you young people just messing your ears up. Shut up. Yeah. So, but you gotta be careful because you could mess your ears up. But I am getting old. I might as well just start to embrace it. Has anyone ever heard of decibels? They talk about like the decibels of this. It could hurt your ears and so forth. Yeah. Decibels are based on log base 10. They actually compare the intensity of the sound you've got in front of you versus the lowest intensity most humans can hear. And they do that, the log of that ratio, and they get decibels. Okay, maybe. Okay. Just to show you a few places, Richter scale, we live in California, you should probably know about Richter scale. Decibels, normally people have heard about decibels at some point. Measure sound intensity through logarithms. Okay. Just to make the numbers easier to, I wouldn't want to talk about the energy of an earthquake being 4,568, whatever the hell. I'd much rather hear a magnitude something. We can kind of internalize that a little bit better. Okay. How are we doing so far? So what does it mean when you see a log without a number in the base? We understood to be base 10. Now, don't say anything. Can you figure out the answer to that question, the one I just wrote? Don't say anything. Well, what are you thinking to yourself? What question are you asking yourself to do this problem? This is everything. This is everything right here. This is how you do any log problem. What's the base understood to be? 10. And what's the answer to a log always? What's the answer to a log always? 2. No, the answer's not always 2. I wish.
That's how many times the number should go to, or can be multiplied.
Yes, how many the number needs to be, or a quicker way to just say it's power.
Yeah.
This sounds like a note, especially when I slow down. That's like a note to write. Every log is a power. The answer to every logarithm is a power. Why am I making a big deal out of that? Like I just said a minute ago. Every property of logarithms is the exact same as the properties of powers because logs are powers. You guys with me? And if you remember, log is a power that helps you remember how to attack a problem. What's the base again? 10. How many 10s do you have to multiply? Or in other words, what power does 10 need to become 1,000? 3. And this is what you really should be desperately wanting from any math teacher is, how do I even think about this problem? Right? It's not memorizing answers. Holy shit, ain't no way you're gonna memorize every answer, but if I give you a problem, how do you attack it? Well, if you know what the question is behind the symbol, you know how to attack it. Log, what power does base 10 need to become inside 1,000? There, you can put together the question. Is everybody with me? Okay, so one weird logarithm, not weird really, but it's sort of like the square root doesn't have a 2. So log base 10, we just don't write it to 10. We just understand it's a 10. Okay. The other weird base, this is where things get nice and weird. Does anyone have their calculator? I have some if you want to borrow one, but does anyone have their calculator? I need some help. I'm going to show you what I consider to be the boring place this comes from first. And then I'll show you the more interesting place this comes from. So what I want to do is I want to investigate. I told you what this here means, didn't I? Didn't we talk about this symbol? So this is basically just saying let n get big in this expression here. So I'm curious, what happens to this expression when I let n get really big? Now let's break this down. If I let n get really big, what's happening to him by himself? This poor little dude right here. 1 divided by 10, 1 divided by 1,000, 1 divided by 1,000,000,000. What is happening to him? And this should sound familiar from our rational functions in finding asymptotes. 1 over n goes to 0, yes? Because the bottom degree is bigger. Are you guys with me? Are you guys all with me? I need you with me. I need you with me. This is really kind of, I need you to understand how cool this is. I know I preface this by saying this is the more boring of the two places where this number comes from, but it's still kind of nifty. It really is. It's just the other way, so much cooler. So if I let n get really big, what does this whole inside become then? If that's going to 0, the inside's getting closer to, you can do it, 1. 1 plus something becoming 0 is 1. We're getting closer to 1. Is everybody with me? So that inside is getting closer to 1. Does it ever equal 1? No. No. It's always going to be 1 plus 1 over something. It's never going to be 1 plus 0, ever. But in the limit, if I keep it going forever, this does approach 0. Now, what is 1 to any power? So you might be tempted to say the answer to this question is 1. You would be very wrong. Because like we just said, is the inside ever 1? Is the inside ever 1? It's always a little bigger than 1. I need you to really see this. So here, let me investigate this. Just looking at the inside. If n is 10, what does that become? You can do it. You can do it.
1/10.
Say again.
10. 1/10 plus 1.
It'd be 1 plus 1/10. And what is 1 plus 1/10? What's 1/10 as a decimal? You can do it.
1.1.
Do it again.
1.1.
So we have 0.1, so let's do 1 plus 0.1 is 1.1. Okay. What if n is, I'm doing this really weird, but it's okay. What if n is 100? We do it like this. What's this become? And what's 1/100th? As a decimal, what's 1 over 100 as a decimal? 0.01. Now, if you can imagine, if I just keep making n bigger, that's just going to push my zeros out further and further and further, but they always hit a place where it becomes 1 at the end, yes? It's always a little bigger than 1. I don't care how big you would again, it's always a little bigger than 1. So, I really, is it important for you to understand what I'm about to say fully in order to pass this class? No. Is it awesome if you understand what I'm about to say? Yes. Okay. The inside, since it never gets to 1, and this power just keeps growing, if the inside was 1, the answer would be 1, because 1 to any power is 1. The inside is never 1. So what they do is they kind of average out. The answer isn't 1, and the answer isn't infinity, it's a finite number. So help me out. Can somebody go ahead and let's do this one thing at a time. If I make n 10, then this would be 1.1 to the 10th. Can you guys do that in your calculator? What's 1.1 to the 10th power? Well, I did bring calculators. Yeah, I think I said that. Yeah. Anybody? Let me know.
2.59374246.
Yeah, 2.5937, blah, blah, blah. What if n is 100? That would be 1.01, like we said earlier, to the 100th power, sorry. 1.01 to the 100th power.
2.704.
Blah, 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 yes? Sweet, thank you. And let's just cut to the chase. Let's do 100,000. Let's see if it can handle 100,000. What would that be, math boy? I don't know. 1, 2, 3, 4, 5. I think it's right. Should be, man. Let's see. 1, 2, 3, 4, 5. Yes. 1, 2, 3, 4, 5. Yes. To the 100,000. Okay, so it's 1.12341 to the 100,000. What do you guys get?
2.718268.
Now, real quick, this is a different idea to us because I don't think we sort of did this with asymptotes. Do you guys agree? Do you guys see how this is not growing faster, right? Do you guys see how it's sort of like settling on something? I don't know if you guys see what I mean. If I kept going, I don't expect this to suddenly become 300 or something. It's going to be 2.7 something in it. Because at 100 it was 2.7 something. At 100,000 it's still 2.7 something, isn't it?
Yeah.
So it seems as if it's settling on a specific number. And that specific number, we called it, sort of like we called pi. When we took a circumference and divided by the diameter, we kept getting the same number no matter how big the circle was. Remember that? I'm pretty sure we talked about that. This number just sort of comes up in a few different places, and this is probably the most boring place, but it's still neat. I gotta be careful how I say that. It's still neat, it's just not as interesting as the other way. We call this number that it would approach, if I kept going, this would approach the number e. Now, just to let you know, a man named Euler came up with this. His name is spelled E-U-L-E-R. But it wasn't because, he didn't call it E because his name starts with E. He was giving variables to different numbers and he just happened to be on E. He's like, he had just said D equal this shit. He's like, oh, this one's neat. I'm gonna call that one E. All right, you guys are on with me. Most of his other ones didn't stick, but this one stuck. How are you guys doing so far? So sort of like pi came from circumference divided by diameter. E fundamentally came from this process. The other place he comes from that I always find much more fascinating is if I graph this function in the first quadrant, it's going to look like for example, 1 divided by 1 is 1. 1 divided by 1/2 is 2. 1 divided by 2 is 1/2. It's going to look like this. You guys with me? So it's got an asymptote here, it's got an asymptote there. In fact, as I write this, I'm like, of course you guys know this shit. Where's the vertical asymptote going to be? 0. And what's the horizontal asymptote going to be? The bottom degree is bigger than the top? Yeah, y equals 0. Yes? So we knew that was going to happen. But here's where E comes out. This is such a tricky thing. I love this. If I start at 1 and if I move a little bit, do you see how I made a little area here? Do you see how there's a little area between the function and the x-axis? The question becomes, how far do I go until this area is exactly 1? And the answer is, if you start at 1, you go up until you hit E. If you stop at E, that area that you got will be exactly 1. When you get to calculus, this will be even a little more impressive because you'll understand how to find the area, you'll understand what the area means, You with me? But at the moment, it's a nice visual idea. Let the area be underneath the function. Where do I stop? So the area is exactly 1. You stop at this mystical, magical E. So it showed up in a few different places, and people are like, we gotta give this damn thing a letter. Remember that pi thing? Let's give this something. And Euler's like, I got you. How's everybody doing? So, can you guys remind me, just to bring this guy into the fold, what was the relationship between these two functions here? What is the relationship between these two functions? You can do it. Come on. Where did logs first show up? Before I even called it a log. Do you guys remember the first time we drew the picture? I don't know if you guys. We drew an exponential, and then we drew its inverse. We drew its inverse, and we didn't even know what the shit it was. We could draw its inverse. So again, how are those two functions related? They are inverses of each other. And just to really hammer this home, I'm pretty sure last time we did a problem like this. Does anyone remember what the answer to that would be? I'm pretty sure last time we had that on the worksheet, we had a problem exactly like this, and I explained it 2 different ways. On one level, this is a really silly question because it's saying, what power does 2 need to become? What power does 2 need to become 2 to the 7th power? Yes. What power do you put on 2 so it becomes 2 to the 7th power? What power do you put on 2? That's a dumb question. You agree with me?
Yeah.
But it's written so that you can just see the answer. If you write it in terms of the base, you can just see the answer. Now, another way to realize this is if these two are inverses of each other, what do inverse functions do when you plug one into the other one? They kill each other. So these kill each other. So of course the answer is 7 because it's the only thing left alive. 2 ways you can look at that problem. Okay, so here's how I'm going to pull E into the fold. E is a remarkable base. Well, let me use it for later. Doesn't matter. So if I have this function here, the neat thing is, whatever number I put in front of the x is related to the rate of increase or decrease. So this is why we often use E to model population growth and like radioactive decay, for example. Because I could see in the power, I could see what rate of growth is. If I saw a 1.4 up here, no, let's 0.14. That would be a 14% rate of increase. If I saw a negative 0.02, that would be a negative 2%, that would be a 2% decrease. Yes? Okay. Over whatever time interval. This is why we love the base E, because if I use it, I could see immediately useful information in the equation. So what does its inverse look like? Well, you guys tell me, based on this fact, that these are inverses, what would this guy's inverse look like? You can do it.
X to the...
No, come on. 2 to the x, the inverse is log base 2 of x. E to the x, the inverse would be?
log
Yes?
E
Base E
X.
of x. Now, writing this, to me, is as weird as writing 2 inside of a square root. Yes, like a 2 instead of just leaving it blank, which we all agreed earlier is a little bit weird. Yes? This is really weird to me. I don't like it. It actually sort of hurts me. Because, all right, do you guys remember what I just said? What is E really good to use to model? It models, throw a couple of rabbits in a room, give them some food, population growth, radioactive decay. Those are both natural processes, yes? So the E function really models natural processes well, which is one reason why they decided to give this logarithm, we never use this symbol, instead we use natural log. ln means natural log. So if you look at your calculator, do you guys see the log symbol? That's base 10. And what's right above the log symbol? Not in your calculator. If you find your log where it says log, you see what's right above it.
I think it's right above.
10 to the x.
Oh,
Like, I mean right above it, you know what I mean? Like,
oh,
to hit shift. Now where's your ln button?
right below.
And what's above that in blue? Or
Into
whatever?
X.
There you go. So they like to put inverse functions with their functions, right? Okay. So the inverse of e to the x is natural log. So what would this be? How do natural log and e to a power, how do they relate? What are they to each other? They are inverses, so they kill each other. So what's the answer? W. That's it. Yeah, W. That's one generalization I want you to take away. If you know a function and its inverse, if you plug one into the other one, they kill each other. You're left with whatever's on the inside. They undo each other. How we doing? Before I forget, this is the natural log. Log base 10, like a log without a, it's a log without a base. Yeah, log base 10, this is called the common log. Because it's commonly used, because we have a base 10 system. I mean, math people were very creative.
This one does natural stuff. It's called natural log. This one happens a lot. It's called a common log.
Okay. Alright, let me make sure. Was there something else before I give you this? There was one more thing, yes. Okay. One more thing, and then I'll give this to you. How would you graph this function here? Well, first off, we know what an exponential looks like. So what's a logarithm look like, considering their inverses? Yes, okay. A logarithm just looks like this. It's got to be mirror image here, so it's going to look like that. So we know the basic shape of it. So I don't need a bunch of points. I only need three anchor points. So you maybe know where I'm going with this. So what are 3 points I can plug in that make sense? Can't plug a negative in.
Oh, yeah. Zero?
Can't plug a 0 in. Do you see how there's an asymptote at 0? So let me help out. I'm going to plug things based on 3. So obviously I'm going to plug a 3 in. I should have gave myself more. But I'm also going to plug a 1/3 in. Yeah, let me do this. I'm going to save myself. I'm going to plug a 1/3 in. I'm going to plug a 3 in. But I'm also going to plug a 1 in. So what is log base 3 of 1/3? What power does 3 need to become 1/3? What do I do to 3 to make it become 1/3?
Negative.
Yes, negative 1. You flip it to become 1/3. So when you need a power to make something flip, it's a negative power. What's log base 3 of 1? What power makes anything become 1? 0. And of course, everybody get ready. What power does 3 need to become 3?
Maybe 1.
First power. Yes? Okay. So it's going to end up with this shape because we've got, I'm going to put 1 here, 2, 3. My scale is beautiful there, Jeff. So if I have an input of 1, it's 0. If I have an input of 1/3, it's negative 1. And if I have an input of 3, it's 1. So it looks like this. I should have made it dotted, but it's too bad for me. Okay. So it looks like what we predicted. Yes? So guess what I could do? The same old stuff. I could do this. I could say, I want you to graph this thing. How would you graph this thing?
Left.
Yeah, left 1. And then down 2. Kick ass. So you take all your anchor points, left 1. God, my scale here sucks. Left 1, down 1, 2. Left 1, down 1, 2. And then this one goes, oh crap. Left 1, dadgummit. Left 1, down 1, 2. Okay. Now where's the asymptote?
X equals -2.
Oh, did I go too far with this one? Left 1, I did go too far. Down 2, it should be here, yeah. Let me make that part of the 2, there we go. So where, the asymptote at first is here, yes? Where's the asymptote now?
X equals
Yeah, because everything went back 1. If I move up and down, that doesn't affect this guy, but this goes back 1. And now you can see these points trying to go like here. Where's he at? Okay, there he is. Show him what there. Wow. Okay, so it maintains the same shape, it just moves. That's how every function does. Not a big deal. You just have to know what the shape is and a few anchor points. Oh, now let me give you guys this. So what I want you to do right now, before I put you in the groups, is kind of look over the whole thing real quick, get a feel for what all the problems are about, and then we'll see about putting you in groups here. All right, let's see. Take a look at it. Kind of glance over the whole thing. See kind of the stuff I'm asking you to do. There's a little calculator section I'm gonna let you guys try out. I pointed out those buttons. If you need to borrow a calculator, I've got some. And then of course I round it off with transformations problem. Down the bottom. 11. No matter, wait, did I just lose somebody? I think somebody just stepped out. How an even number of people maybe?
Give me the math one.
Huh? 12. That's right, okay. I was about to say, you guys, no matter how many come, it's always an odd number, but not today. So let's see. Let me do, let's see, so everybody get ready to move, potentially. So you guys might get lucky and get to stay where you are. Let me get Trent and Buddy. And let's see, Trent and Ilya, you three here. Alright, so maybe come up here. Turn around and you can stay right where you are. These guys can move, or you can move. And then let me get. Let's do Layla and Charlotte in the back there, and Zhayu. Right, you three. So
I got to
wherever you guys want to be, you can go back there with Charlotte, or you can come up here with these guys. These two. If you guys work together, meet somewhere. Oh, Dylan. Oh, that's right. Okay. Do I have 13 now? Maybe. If Angela, let me get you to work with Dylan and Where's Sean? So maybe you guys come up here. Anywhere in there is good. Who have I not put for people yet? Sorry. Can I get, let me see, yeah, can you work with those guys? Oh, no, Angela, did I put you with somebody already? Yes. Who's not been set with somebody yet? Wait, just left you guys? Alright, everybody get to work with me, and then I'll figure it out. Who are you working with? What has happened? Did you just put yourself there? Come here, come here. Yes. You're gonna work with these guys. And then you, I did end up with an odd number two, so you can join any group you want. You're that lucky. So they won't take it bad. Go for it. Alright guys, let me or Christine know if you need some help. Go ahead and try to do these problems. Please, dear God, help each other out. And talk about what's going on. Yes?
When this is before the what do we?
Oh, yes, I remember. Alright. What functions do you have? You have 10 to a power.
Yeah.
And you have log base 1. No, you have log of 4. What's the base?
This
Understood
is
that. And what happens when you put a function into its inverse? Okay, good. So what dies is that? What are the inverse functions?
In this one, we have log 10. Is that?
Yes, and that's the inverse of 10 to a power. So what's left alive?
Wait, so it's 10 to the power of.
Totally.
That's confused.
So-
Yeah, okay. 10 to the power of log.
You ready? So one function is 10 to the x, and what have you plugged into that function? What have you put? So if you have a function 10 to the x, what have they put here? They put something into this function, didn't they?
Yeah.
They being me. What did I put in there?
Okay.
What did I put in there?
4.
No.
Yeah.
What did I put here?
10.
No. What does it say? What's the problem? 10 to the?
Log.
Yes. So what did I put in place of this?
Log.
Log 4. And how is this related to this? They are what of each other?
Inverse.
And what do they do when you plug one into the other one? What do they do to each other? Cancel. So what's left alive? Yeah, you're done. There you go. I am going to show it a different way to think about it, but that's the most immediate way. Just,
Right.
It's sort of like take cube rooting a cube. Same idea, yes?
Yeah.
Okay.
Now E.
That's cool.
What makes it go smaller?
Smaller.
We get from 16 to 12. Because this is looking like 16 x. And then you get 1. We'll see. I didn't have time to do it today, but yeah. It might even have battery. Yes. Oh, yeah. So this here is your tuba. Yeah.
So he's three. Then you hit the tuba, and then you just put 2 pieces. And then like element is right there,
Oh, yeah.
and log base 10 is right there. Just erase this. And you just put that, yeah, just put that in there. Yep. Doesn't matter. You only need to close it if there's more after it. If you don't close it, the calculator understands. Yeah. Yeah.
How do you?
All right. I know you guys are just now. We're gonna let me catch up to you guys. Okay. Now, I don't mind, I don't know if you've noticed, we're spending a little more time on logs. They're huge. They just come up everywhere. You have to know, kind of like, you have to be comfortable with them so when they show up, you don't go, ah! Because they're going to come up a lot in, I don't know, calculus. Yes? We use them in a lot of ways. They are so freaking useful. And you'll see one way they're useful when we start solving equations using logs. So at the very beginning, do you guys remember, and this is from my last semester 171 class, one of my students came up with this, put it in the washing machine. Have I said that to you guys yet? Maybe. Okay. Here, can you guys remind me, what is log base 3 of 27?
3 to the actual 4.
So 3 to the what power is 27? How many 3's multiply to be 27? 3. So I want you to realize there's two layers here. There's two layers. Logarithm is asking you for power. What power does the base need to become this? Yes? If you internalize that, you have a way to attack it. So what you said was beautiful. You said 3 to the x is 27. Do you actually have to write that down? Not necessarily. 3 to what power is 27? 3 times 3 to, 3 to the third power is 27, right? You have a way to attack it. You're not supposed to memorize this shit. Do you think I have every one of these memorized? No way in hell, man. I ain't got that much room up here. Got a tiny little brain. So, sorry. Why is this true? What's another way to write this to represent what we just did? 3 to the third power is 27. I can always rewrite a logarithm as an exponential because that's where the answer came from. The answer is the power it needs. So last semester, my students called this the washing machine. Yes? If you don't like that, it's fine. One of my colleagues calls it the snail. That doesn't make any sense to me, to be honest, but I like washing machine. So like base, what's the output to a log always? The power. The power that what? That the base needs to become this. Right? And now I've got the power of voodoo. Who do? You do. Do what? Oh, sorry. That's from the movie Labyrinth. You don't have to watch it. So looking back at this, how do I rewrite this? What's the base? What's the base? 3. What's the power?
10.
So 3 to the 10, that's what creates y. There, done. 3 to the 10 equals y. Put it in the washing machine, right? Stay with me now. I want to point out something. What was the input to log in the original problem? What was the input? What was the input to the log in the original thing? You can do it. What did they put into the log? What did they put into the log? Y. And what was the output in the other way to write it? Y. Because these are inverses of each other. What do inverses do? It makes one guy's output become the other guy's input. What's the output here? 10. What's the input here? 10. It took one guy's output, made it the other guy's input. That's what freaking inverses do, yes? Okay, maybe. So the answer to a log is the power the base needs to become the thing on the inside. That's why this idea works to rewrite it. It's always easier to rewrite a logarithm as an exponential because you can do this than it is to write an exponential as a log. It's a little bit less straightforward. But can somebody tell me what the base is on number 2? What's the base? 7. So I know that much. What was the output?
5.6.
So now that's the input, and what was the input? So now it's the output. See? That's not that bad. And then you can check yourself. 7 to the W equals, is that right? 7 to the W, yes. So you can always check yourself after you write it. How are we doing so far? So in the middle of writing, you can kind of make sure, am I going the right way if I just put it in the washing machine? Do I get what I'm supposed to get? Real quick, just to show you, we spend so much time on this, but we don't spend it like here, what's the cube root of 8?
2.
Can you write that a different way? Why is the cube root of 8 2? Because 2, no, 2 to the, there, that's exactly what we just did. We have it written with one function, and then we rewrite it with the inverse function. What's the inverse of cube rooting? Cubing. What's the inverse of
Logging,
Exponent.
planting trees. No, the inverse of logging is exponentials. Yes.
Yeah.
I don't know if you really are with. And again, I know this whole thing is a little new, or you've seen it before and you hated it so much. I understand. But it's exactly everything we've done before. This is you guys know this inherently. You didn't even have to think about it. But it's all we're doing here. Why is this one harder? Because logs, we don't use them as much. We're not as used to them. All right. What's log base almost anything of 1? What power does almost anything need to become 1?
0.
0.
Yeah.
So appreciate that.
Just gonna,
What do these two do now that we know the relationship?
they're inverses, so they.
Yes. Natural log is the inverse of e to a power. And I took one of them and I put it into the other one, therefore they kill each other. Did I start the camera back up? Thank you. So then, die, what's the answer?
Pi.
Pi. Die pi. Sorry. This one's really, really nice. Even though I put pi in there, who cares? What power does pi need to become pi? 1. Choo-pa-choo. This one is exactly the same idea as this one. Where's my finger? There it is. This one is the same idea as this one. How does log relate to 10 to a power? How do these relate to each other?
They are.
They are
Inverses.
inverses. Dun, 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 dun. So if I plug one into the other one, what do they do to each other? Kill each other. So I don't care. If I have two functions that are inverses, I don't care which one I put into the other one, they will kill each other. That's why we call them inverse functions. They undo what the other one did. So over here, I put an exponential inside of a log. Over here, I put a log inside of an exponential. Either way, you just get whatever's there. Now listen, is everybody with me on that? I need you to understand. I cannot stop myself from explaining it to you one other way. If you understand this, do it this way. What does this mean? What does that represent?
Log 10 to the 4.
What does it represent? What does every log represent? What does every log represent? An exponent. Kick ass. Every log represents a power. Specifically the power that what needs to do what?
Get that.
What's the base?
10.
So this right here represents the number that you need to put as a power on 10 to make it become 4. Let me say that again. I need you to really get this. Does everybody see that? I've said this before. The output to this, whatever this is, whatever number this is, it's the power that 10 needs to become 4. Is everybody with me? Whatever number, if you plug this in your calculator, you get some funky ass decimal number, yes? And when I put that on 10, in fact, I'll show you that in a minute. So what happens, if that is the number that 10 needs as a power to become 4, what happens when I put it as a power on 10? It becomes stupid 4. That's what the point is, yes? Now, listen. You don't have to look at it the way I just explained it.
Oh.
But I love, okay, that is a power. The power 10 needs to become 4. So of course, when I put whatever that number that is, when I put it on 10 as a power, it becomes 4. That's what the hell it does. That's its purpose, right?
Yeah.
Maybe. So let me show you. So if I do log 4, I get a number. Log 4. Bam, I get that number. Look at that number. Gaze upon that number. Now, if I do 10 to that number, and I'll go ahead and just type it all in so you can see it. It might not come out to be exactly right, because hopefully you understand this keeps going forever. This should come out close to 4, if not 4. All right, good. Do you guys see what I mean? The log is the power 10 needs to become 4. So, of course, when I put it on 10 as a power, it becomes 4. All right, I'll stop. You don't have to look at it the way I just explained it, because they just kill each other, yes? They just freaking kill each other. Yes, that's all you need to know. But I love explaining the other way because it reinforces what logs are. What about this dude? Don't just tell me the answer, tell me how you figured it out, somebody. Did any group figure out part E? Anybody? You did. How'd you get it? How'd you get it? Do you know? You're like, I don't know. I wasn't there when I did it.
So, you just, I'll just go how you explained it last time.
Yes, go ahead.
You did like 16 to the x.
Good. So I don't know what it is. So then you can put it in the washing machine.
And then you said the 2 to the 4th.
Good. 16 is 2 to the 4th.
Times x equals 2 to the 1st.
Good.
So you just,
And the only way these could be equal is if the powers are equal, and then you get your gigas, right? Did anyone do it the other way? Where you take 16, I think at least one person did, break it down, and 2 is how many out of these 4? How many of these do I take to make 2? 1 out of 4. That's why the answer is 1 out of 4, right? Do you guys see that? That's a valid way to do these problems, by the way. Now, I talked to one group about part F. What do I do to 16 to make it become 2? I raise it to the 1/4 power, yes? You with me? If I raise 16 to the 1/4 power, it becomes 2. This asks me to go one more step. Now make it become 1/2. And the answer is right in front of your face. How do I make anything flip? Negative power, yes? So 16 to the positive 1/4 is 2. Therefore, 16 to the negative 1/4 is 1/2. Now, if you want to do the work, you would say 16 to the x equals 1/2. This would be 2 to the 4th x is equal to 2 to the negative 1, yes? And then 4x equals negative 1, and then you finally get negative 1/4. Okay. But if I know this is true, then to flip it, I just have to make it become a negative power. That's going to do the one more thing. It's going to make it flip. Okay. Either way you can think about it. Now, part G, I want to remind you guys, because this becomes really important in calculus. You have to really just know this shit. Radical notation should never have been invented. It is one of the dumbest things we did. And I think we were especially drunk that day or something. What's so much better, and you guys don't want to lose it. I know, I don't blame you, because that's what you're used to. You're like, I've seen radicals my entire life, man. What do you mean get rid of them? But they just suck. More commonly, and Christine can back me up, or she could say that, no, Jeff's being crazy. You almost always, especially starting in calculus and so forth, you don't want it written as a radical. How do I rewrite this? That's the question. How do I rewrite this as a power?
11 to the 1/5.
Yes, because what's a fifth root doing? Cutting it in 5 parts, yes?
Yeah.
Multiplicatively. So that's why I put a 1/5 in the power to represent cut it in 1/5 multiplicatively. And now it becomes a stupid problem, right? What power does 11 need to become 11 to the 1/5? Or you could just do this. What do these do to each other? This function and this function cancel, so your answer is 1/5. What do you raise 11 to make it become 11 to the 1/5? You raise it to the 1/5. That's the other way to look at that problem. Okay. So basically, a huge takeaway from everything we've talked about is when you see logarithms, you think powers, because that's what they are. And then that shows you how to think about the problem you're looking at. These are just plug in the calculator. I almost don't care. But you have to know how to do this. So like, for example, this is your to the button right here. I call it the to the button. So if I do 3 to the, what was it, 2.16, I get that. Did you guys get that? Okay, good. I was worried about my poor little calculator. How's he doing today? Apparently so far so good. Natural log of 111. That's not bad. You got your natural log button, and you put 111. Enter. Somebody had a good question. Do you have to close a parenthesis? Obviously not. You only have to close it if there's more shit after it. Yes? Is that what everybody got? What does that mean? What does that mean? What's it mean? And you're like, yeah, I don't know, 4.7. What's it mean, considering what it's the answer to? What does this represent?
E
Yes,
negative
it's a log, so what's it represent?
equal
A log represents a power, the power that E needs to become 111. That's what that is. If I raise E to this number, it becomes 111. So if I raise E to the Jeff, I saw there were numbers there. 4.7095 30201. There, right? Okay. So you want to make sure you can interpret what you just got. Yes? It's not just numbers doing shit. They're numbers specifically that do something specific. In this case, that 4.7 number makes E become 111 if I put it as a power. Okay. And then we got this thing, so we got my log button. 0.4132. Shabam. Negative point. What did I say? Round it to the nearest hundredths place? So it should be negative 0.38.
It's so there's the letter E, and then that has like this.
Okay. And then this one, I think I got around to at least a couple groups. But if you remember, an unshifted log, this is why this is so important. I can't stress enough the importance of this. If you know the shape of functions, you can handle so many more things. So a basic log that hasn't been shifted, where's the asymptote?
0, 0,
Huh?
0, 0.
No, that's a point. An asymptote is a line.
0.
Huh?
Y equals
No, that would be this.
X equals
X equals 0. Good. You had a 50-50 shot. So this is x equals 0. Is that cool? And of course, up and down is x equals, because if I don't let it go left or right, I control x. I make x equal one thing. Then it can't move left or right. That's why it can only go up and down. That's why this is x equals. So there's an asymptote at x equals 0. So what kind of inputs am I allowed to use for an unshifted log?
positive.
I can only plug in positive numbers, correct? 0 freaks it out. That's an asymptote. It can't go there. And negatives definitely freak it out. That's on the other side of this barrier. There's nothing over there. Yes? Okay, I like it. So what is inside the log we're looking at? What's inside of it? What's inside the log we're looking at? X plus 2. The inside, what did we just say has to be true about the number inside the log? It's got to be,
It won't ever change. Yeah.
what's got to be true about the number that we plug into a log? What did we just say?
Has to be positive.
Positive. What's a mathematical way to say positive? Greater than 0. So the inside has to be greater than 0. We've seen this before. How do you find what's the domain of this guy? What's this guy's domain?
Wait. 7 to infinity.
Let me ask you this way. What do I throw out? What is this guy not allowed to use? Why? Bottom can't be 0. So if you just write what you just said, if the bottom can't be 0 and you solve it, you get the domain. X can't be 7. So you were half right, you just left off the negative side. Yes? So if you say in English what must be true, the number inside must be bigger than 0 for a log, and then you solve it, you got your freaking domain. You got the values of x that make what you just said happen. That's awesome. And that really highlights how math is a foreign language. I said in English, and then it translated to Mathish, and then I can solve it. What are the transforms? It's really just one. What's the one transform I'm doing?
Left 2.
Left 2. So if I graph the base function, it always goes through 1, 0. It always goes through the base 1. And it always goes through 1 over the base, negative 1. Those are the 3 anchor points for logarithms. And then I have a asymptote here to begin with. I take every point and I go left 2. 1, 2, 1, 2. Careful with this one. 1, 2. And where's the asymptote now? X equals -2, because everything moved back 2, including this infinite asymptote. And then I got this dude. Weehaw! Same exact stuff we did when we first learned transformations. We did it with parabolas, then we did it with absolute values. It don't matter what the function is, they all work the same way, which is almost too nice to believe. Hooray. Okay, so any questions from this whole thing? These are exactly the kind of questions I like to ask you on quizzes and tests. Hint, hint. Okay. So, if you want to, you can stay where you are. You can go back to your seat. It don't matter none. We're going to talk about one more idea, and then we're going to head out. This idea might take a little while, so I'm going to... So whenever we come up with like a new function, we want to talk about how does that function work. Like square roots. If I said square root of 2 plus square root of 3, oh dear, is that square root of 5? Square root of 2 plus square root of 3, does that make it become square root of 5? I'll tell you this, the answer is no. That's not how square roots work. Yes, they're not like terms, you can't put them together. So I need to know, when I have a function, I'm curious, how does it interact with itself? Like if I add 2 logs together, something special happen. If I have a log with a bunch of shit on the inside, can I do anything to simplify it? Like what do I do? Remind me, what do I do with like the square root of 20? What's the property of square roots that I could use? How do I simplify the square root of 20? Yes, square root of 4 times. Good is a property of roots that if I multiply the same root, they can go together, so I can break them back apart. So this is what I mean by properties of logarithms. What can I do if a log has a lot of shit inside of it? What can I do if 2 logs are adding to each other? All this kind of stuff, yes?
Yeah.
Okay. If 2 logs are multiplying or whatever. So the very first one I want to investigate is what happens if I have the log of one thing times another thing. Like what if I put into a log 2 things that are multiplied? Yes? I'm curious, is there a way to kind of simplify it? Sort of like we did with square root of 20, it was 4 times 5 inside of the square root, and there's a way I could simplify it, correct? You guys kind of follow what I'm saying? If I put 20 into a square root, 20 is 4 times 5, I put a product of 2 things into a square root. And then we had a process we could use because of how square roots work. Now I'm curious, what about logs? Logs feel a little bit like roots. So what happens when you put a product inside of a log? Okay, so let's see. Let me call the answer, well, let's see, how do I want to approach this? Yeah, okay. What if I call, I'm going to call log A, I'm going to call it M, and log B, I'm going to call it N, just because. What is A equal then? Can you solve this for me?
10 to the n.
Yeah, 10 to the M. And what's B equal? 10 to the n. So what is A times B?
10 to the m times n.
Yeah, A is 10 to the M. B is 10 to the n. Okay, let me stop for a minute because this is weird whenever I start doing proofs. So what did I just do? I said, all right, let me investigate parts of this. So let's call log A something. And then I can actually solve for A. Let's call log B something, right? So what does this kind of represent? This represents everything, every possibility. So now I know, and what happens here? What do I do when I multiply like bases? What do I do with the powers? Yes? So then I can investigate. Now look what I could do. Look what I can do. I can investigate this directly. What is log of A times B? Isn't that what we want to know?
Yep.
Okay. So what is A times B again?
M plus
No. What's A times B?
10 to be
10 to the. All right, let me stop for a minute. You're never going to have to do this yourself, but I just want you to follow along. I want you to see where this property comes from. I have no idea. I'm always curious what this looks like to you guys. It's got to look a little bit like a jumble. And I'm sorry, but it's pretty cool. I just said, I don't know what that is. I'm going to call it M. And I just sort of followed it, yes? I don't know what it is. I'm going to call it N because I know they're probably not the same thing. I'm going to follow it. And I'm like, oh, cool. I got A times B, and that's exactly, I want to investigate A times B. Let me plug this shit in. Now, what's the base?
10.
10. So what is log base 10 of 10 to this?
M plus
These kill each other, yes?
yeah.
Die. So this is M plus N. All right, now hold on. Man, derivation in math. I know students, I know you guys probably dislike it. And part of the reason you dislike it is because it's using things that you're just getting comfortable with. I don't blame you. Yes? We're talking about things you're just getting comfortable with. But nothing I've done here is stuff we haven't done yet. We've done all of this. Can somebody remind me, please? Let me write down what we got so far. What was M? What did I say M was? From the very beginning, what was M? No. What was M? What was M?
Log
No. Log A. And what was N? Log B. Look what we just proved. We just proved that the log of a product is the sum of the logs. I can break it up. That is not obvious, but let me show you what this really says. What do I do with the powers when I multiply like bases? What do I do with the powers? Don't both of these have a base of 10? So what do I do with the powers when I multiply like bases? What's x squared times x to the 5th? X to the 7th. You add them, correct? Okay, so let me say this again. What do I do with the powers when I multiply like bases? I add the powers. Yes? What is a log? A power. So all the properties of logarithms are the same as the properties of powers. When I multiply things with like bases, I add the powers. So what do you think, without actually proving it, where do you think Jeff put his glass? There it is. Okay. What do you think log of A divided by B is? You could do it. You could totally do this. Yes, subtraction, of course, right? Because what do I do when I divide like bases? I subtract the powers, correct? Same exact idea. So this will be log A minus log B. Just in case you're not picking up on this vibe, you have to memorize these. But if you know the properties of powers, you know the properties of logs because they're the same thing. No, I want to go one more step. I want to investigate this guy. And this third dude is the most important dude, but that means this guy is the most important because he wouldn't exist without this guy. So here is the one we're going to use the most. What would log of A times A times A, basically what would log of A to the P? Like if I have P of these, PAs, does it make sense? I got so many variables, but if I have a string of PAs, maybe P is 7, P is 20, however many A's I got, you guys with me?
Yeah.
So this is basically log of a to the p. A times a times a, p times is a to the p. Is that cool? A times a is a squared because there's two of them. A times a, p times is a to the p. Does something happen there? And it feels like it should, because what are logs all about? Yes, powers. Exponents, yes. So it feels like this should simplify because you got a power inside of something that deals with powers. So let's see how this works. Coming from this guy. If I have log of a times a, that's log a plus log a, using that first property, yes? And if I keep going, I would just keep adding. And I would add, how many of these would I have? How many of these did I have?
P.
P of them. So how many of these will I have?
P.
P of them. Okay.
Log A times.
So again, log of a times a is log a plus log a. So log of a times a is log a plus log a plus log a, and I just keep going. Maybe. How do I do? What's log a plus log a? What's just log a plus log a? What is that?
Log A times P.
No, come on. Well, yes, but say it better. What's x plus x?
Is log 2x.
Yeah, so 2x, so 2 log a.
Okay.
And what's log a plus log a plus log a?
3 log
3 log a. What's log a plus log a plus log a? P times.
P log
P log a. Affectionately called plog. So look at what happened. We started with this thing, yes? What effectively happened? What is a log? What effectively happened? Where did he go? He effectively came out front. Now, why does this make sense? Does everybody agree P is a power?
Yes.
Does everybody agree log A is a power? What do you do with powers when you raise something with a power to a power? You multiply them. That's why this is one power times the other one, because I'm raising something with a power to a power. What do I do with the powers? I multiply the powers. I promised you, every property of logs is a property of powers because logs are powers. And I know I keep saying that because it needs to get in your head. If you know logs are powers, everything about them makes nothing but sense. I'm not saying every problem's going to be easy. I'm saying it's going to make sense. You're going to have an idea of how to attack it. Okay. So how is any of this useful, dear God, Jeff? That's a good question, right? Let me show you one example of a concrete reason this is useful. Does anyone know what log base 12 of 3 is? Do you just know what that is on your off the top of your head? What would it mean? What would log base 12 of 3 have to be? The number that does what?
Multiplies 12 to the power.
When you raise 12 to it, you get 3. Do you understand that's got to be a really funkadelic number? Does everybody agree with me? 12 to the what power is 3? We're like, I don't freaking know. Okay, I agree. Does anyone know what log base 12 of 4 is? Same problem, correct? Exactly the same problem. All right, so I don't have a clue what this shit is, and I don't have a clue what this shit is. But why can't I suddenly do this problem? What did this rule say? If I have the sum of 2 logs with the same base, how can I rewrite it? So this would be log base 12 of 3 times 4. Yes. So this is log base 12 of 12, which is freaking 1. So we came from 2 numbers we had no idea. We just know they're gross. But because of our property of logarithms, we're actually able to do this by hand. I didn't need a calculator for this shit. That's one of the most immediate uses of the properties of logarithms. Now, this doesn't happen very often, so thankfully there are more uses of them, but we just barely got into it. So next time, meaning tomorrow, we first have the quiz. Yes? We have another quiz tomorrow. If anybody didn't get their quiz back, just see me before you leave. And then after that, we'll keep going with properties of logs and see how far we can make it.
I will see you all tomorrow.
Okay. Cheyenne. Chibon.
I collected all of it.
Oh, sweet.
Thank you, son.
What's the quiz on that? Like, what